Thank you for the introduction. And I have been attending this seminar for last couple of years, and it's feel really nice to be on the presenting side today. I like to thank the organizer for their kind invitation and opportunity to speak today. So in this talk, I'll present our recent work. It's a joint work with my supervisor, Bardharaj Ravi Srinivasan, and it's about how differential Galois theory can be used to study nonlinear differential equation. And the reference for this is this article of the same title as the title of the talk. I would also like to mention another work of ours, classification of first order differential equation. So whatever I will be discussing for algebraic differential equation, for first order differential equation, all the results follows from this article. And basically this article is the starting point of our work. And in a way, this article is more intuitive than I would say. Okay, so let's start with some basic notation and some basic definition. So K will be a differential field of characteristic 0 with a single derivation, which I denoted by prime, and the subfield of constants of K is C, which assumed to be algebraically closed. The field of constant of a differential field extension E of K is denoted by CE. Strongly normal extension is a differential field extension which is finitely generated having same field of constant as K, and it's satisfying the following normality condition. So if sigma is a differential K embedding from E to M, where M is also a differential field extension of E, then the image of E under sigma is contained in ECM, where ECM is the field compositum of E and the constant of MCM. So Kolchin defined this strongly normal extension as a differential analog of finite normal extensions. So these extensions has very rich differential automorphism group. Before that, an example, a Picard-Bessel extension for a linear differential equation is a strong normal extension. So all Picard-Bessel extensions are strongly normal. And the group of all differential automorphism of a strongly normal extension called the differential Galois group of the strongly normal extension uh, is an algebraic group. So they have very rich structure of differential automorphism group, and it's an algebraic group over the field of constant C of K. And then the Picard-Bessel extension characterized by strongly normal extension with differential Galois group, a linear algebraic group. Here are a few easy examples. So consider this field Cx, the field of rational function in one variable over complex coefficient with derivation d dx. Then K exponential of x is a Picard-Bessel extension for the linear differential equation T prime equal to T with Galois group isomorphic to the multiplicative group. And the next example, K y prime, where y satisfies this differential equation y prime square equal to alpha square multiplied by 4y cube minus g2y minus g3, where alpha in K, g2, g3 in C, and we also have the non-singularity condition. So it's a strongly normal extension of K with Galois group isomorphic to the elliptic group, the C points of elliptic group. And this is an example of a strongly normal extension, which is not a Picard-Bessel extension. An iterated Picard-Bessel extension is an iterated strong normal extension or iterated Picard-Bessel extension is a tower of differential fields K E naught containing E1 under En minus 1 equal to E. So a tower of strongly normal extension or a tower of Picard-Bessel extension is called iterated strong normal extension or iterated Picard-Bessel extension. So for example, elementary extensions, Liouville extensions, those are iterated Picard-Bessel extension, in fact. An algebraic differential equation over K of order n is an equation of this form f of t prime dot 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 t nth derivative of t equal to 0, where we assume that f is an irreducible polynomial and its del f del xn not equal to 0. So it's an equation of order n. And by solution of the equation, we mean an element y in a differential field extension f of k with the constant are same, Cf equal to C. C is the field of constant of K, such that it satisfies the equation. And by a solution field, we mean a differential field generated by a solution of the equation. So it's a K angle bracket Y, that means it's a field generated by K and all its derivative. Particularly, I want to talk about an particular example of algebraic differential equation is Riccati differential equation, and which will be appear many times in the talk. So let L of t equal to 0 be a linear differential equation over K and W be a new variable, and you define t prime equal to Wt. If you differentiate this relation and substitute those in LT equal to 0, then you get a nonlinear differential equation over K, which is denoted by RLW equal to 0, which will be of order n minus 1. And this is called a Riccati equation associated with L. So for example, if L of t is a second order linear differential equation, then the corresponding Riccati equation is a first order equation of this form, W prime plus A1W plus W square plus A naught equal to 0. Where A1 and A0 is the coefficients of the linear differential equation. And it's very easy to see that if y is a non-zero solution of the linear differential equation, then the logarithm derivative of this solution is a solution of the Riccati equation. So the solution of a Riccati equation is essentially a logarithm derivative of solution of a linear differential equation. Okay. So what we do is we explore connection between solution fields of algebraic differential equations and strongly normal extension to study how the structure of these fields relates to solvability and algebraic dependency of solutions of an algebraic differential equation. And we thought in this line because there are certain results that illustrate the role of strongly normal extension in the study of algebraic differential equations. And I'll briefly explain some of those results. So the first result is independently proved by Goldman and Singer in these articles. So and the result is let K be an algebraically closed field and Ky be a solution field of a first order algebraic differential equation f of t prime equal to 0. If y is also a solution of a linear differential equation L of t equal to 0 over K, then K containing Kz containing Ky. So the solution field has a differential subfield Kz where Z satisfy either Z prime equal to Z satisfies Z prime equal to Az plus B, where AB in K. And if L is irreducible of order n, then this linear differential equation has a basis of solution which satisfy yi prime equal to ai yi. So So if you consider the Picard-Vissou extension of this linear differential equation, then this algebraic differential equation f of t prime equal to 0 has a solution in that Picard-Vissou extension. And this result is basically about solvability of a first order algebraic differential equation in a Picard-Vissou extension. And if the linear differential equation happen to be irreducible, then it also says about the solvability of the linear differential equation. Even it says more. So it is easy to see that the differential Galois group of this L of t equal to 0 is a torus. The connected component is a torus. So this is about solvability of an algebraic differential equation in a Picard-Vissou extension. The next result is by Rosenlied in this paper, the non-minimality of differential closure. So it says if you have a equation t prime equal to f of t over c, the field of constant, and suppose that M is a differential field extension of C such that MT, where T is transcendental over M and T prime equal to f of T, this MT differential field has a constant which is not in M. Then CT has a differential subfield CZ where either Z prime equal to 1 or Z prime equal to CZ for some non-zero C in C, which equivalently 1 by F to be of this form. Either it is a derivative of an Z in CT and or it's a C multiple of a logarithm derivative of an element in CT. So, the connection between connection to strongly normalized extension is that this CT contains an strongly normal extension, which is CZ, Z prime equal to 1 or Z prime equal to CZ. And a very nice application of this result is that one can prove that this T prime equal to T, T prime equal to f of T has either one or infinitely many algebraically independent solution in a differential field extension of C with no new constant. So if f is either a derivative or a logarithm derivative of an element in CT, then it's very easy to see that it has only one algebraically independent solution, as in that case, CT contains an element whose derivative is either 1 or it's a Z prime equal to CZ. And if f of t is not of those forms, then one can show that it has infinitely many C algebraically independent solution. By that I mean for any natural number n, there exists a differential field extension which is no new constant extension and contains n algebraically independent solution of this equation t prime equal to f of t. And it's very it's basically if you define a, so you consider this differential field CT and T you define to be an indeterminate and then define the derivative of T to be FT, then it will be solution. And if you continue doing the same process, you will get a differential field with as many as you want algebraically independent solution. So for example, these two equations, T prime equal to TQ minus T square and T prime equal to T over T plus 1 has infinitely many algebraically independent solution. The next result is about Penlevy equation. So Umemura defined that a function fx is said to be classical if it belongs to an iterated strongly normal extension of Cx. And he provides a condition called Umemura-J condition, which proves that the solutions of the Penlevy equations are not classical. And this condition, this Umemura-J condition, is basically an application of an intrinsic characterization of differential subfield of strong normal extension, what they call differential field depend rationally on arbitrary constant. So we have seen some results which related to strongly normal extension and used to study algebraic differential equation. So what we do is that, what we did is that we provide a structural characterization of differential subfields of strongly normal extensions. And we obtain a new perspective on the results of Goldman, Singer, and Rosenlit. This is, I'm saying, because the proof of this result, Goldman and Singer. So the proof of Goldman result uses some differential polynomial results from the works of Reed. The proof of Singer's uses differential valuation, and Rosenlet use one forms and that D1 map. And it's basically using some property of an algebraic function field in one variable. And we connect this result to differential subfield of strongly normal extension, and we reprove and extend them to higher order equations. We then study the differential algebraic dependency among solution of an algebraic differential equations. And we provide a necessary condition for an algebraic differential equation to admit a generic solution in an iterative strong normal extension. Here, generic solution means a solution whose solution field has same transcendence degree as the order of the equation. Okay. So the transcendence degree 1 differential subfield of strong normal extensions are known, which we have this result is proved in this paper, a classification of first order differential equation. So our transcendence degree 1 differential subfield are nothing but differential field generated by first order recurrent differential equation or this first order differential equation. So it is either a abelian extension. So this KYY prime is an abelian extension. So strong normal extension with differential Galois group and abelian variety, or it's a Riccati equation. Okay, let's move on to the main results. So to define or to characterize differential subfields of strongly normal extensions, we define these fields we call irreducible differential field. So a finitely generated differential field extension f of k having transcendence degree greater than equal to 1 is said to be k irreducible if every differential field intermediate to k and f has either transcendence degree 0 or it has the same transcendence degree as the transcendence degree of f over k. And then any differential field extension whose transcendence degree 1 is irreducible, and if it is a differential field of transcendence degree greater than equal to 2, then you can resolve into a tower of differential fields where each component of the tower is irreducible. And then basically understanding this irreducible differential subfield of strongly normal extension are enough to understand any differential subfield of strongly normal extension. So this theorem of ours characterizes differential subfields of irreducible differential subfields of strongly normal extension. So let E be a strongly normal extension of K and cannot be the algebraic closure of K in E, and F is a K irreducible differential subfield. Then either K naught F is an abelian extension of K naught, or F is a finite algebraic extension of KW, where W is a solution of recurrent differential equation over K. And if K has trivial derivation, that is K equal to C, then B can be replaced with B star, which is F equal to CZ, or either Z prime equal to 1 or Z prime equal to CZ for some non-zero C in C. Okay. So the proof of this theorem is lengthy. So I will just outline the proof. So in the first part of the proof, what we used is basically some nice result from algebraic group theory, and it's some nice structure theorem of algebraic group. So let G be a connected algebraic group, then there exists a maximal connected normal linear algebraic group N of G. So the factor group G mod N is an abelian variety. And the second structure theorem is that there exists a smallest normal algebraic subgroup D of G, whose quotient is a linear algebraic group. So now let E be a strong normalizations with Galois group G. Then corresponding to this structure theorem, there is a structure theorem of this strongly normal extension. And if F is an irreducible differential subfield of E, and H be the corresponding subgroup of H, we consider this homogeneous space V G mod H, and let A be its Albanese variety. Then a result of this article by IISER shows that dimension of the Albanese variety is less than equal to dimension of V. And because of irreducibility of F, we show that dimension of A equal to 0 or dimension of A equal to dimension of V. And again, using some results of IISER, in the first case, D must be contained in H, and the second case, N is contained in H. And this proves that K naught F is an abelian extension of K naught, or K contain F, contain L, contain E, where L is a Picard-Hessian extension of K. So any irreducible differential subfield of a strong normal extension, either an abelian extension or it's a differential subfield of a Picard-Hessian extension. And to characterize irreducible differential subfield of Picard-Hessian extension, we use this unipotent radical and the radical of the group. So we consider this field LU, the fixed field of the unipotent radical, LR, the fixed field of radical. And we saw that because F is K reducible, one of the three cases is possible. The F intersection LU is equal to K. F is contained LU with F intersection LR equal to K. And the third one is F containing LR. So we handle these three cases with three different lemmas, and in first two cases we use the structure of Picard-Hessian extensions with differential Galois group, unipotent and torus respectively, and the proof is essentially finding some invariants, some nice invariants satisfying some nice differential equation. And the third case we handle by analyzing maximal connected subgroup of a semi-simple algebraic group. So note that LR is a Picard-Hessian extension of K with differential Galois group or semi-simple algebraic group, and the irreducible differential subfield corresponding to maximal connected subgroups. Yeah. And then we also have a structure theorem for differential subfields of iterated strong normal extensions and iterated Picard-Hessian extensions. So if F is a differential subfield of a iterated strong normal extension, then F can be resolved into tower of differential fields where each component is a differential subfield of a strong normal extension, and the same hold for a Picard-Hessian extension also. Okay. Now we'll move on to the application of these two results to algebraic differential equations. Okay. The first one is that extension of Goldman and Singer's theorem, and we need the notion of D-solvability defined in this paper of Nguyen. A similar kind of solvability also defined by Singer, and for D equal to T, he called those extensions Eulerian extension. So a solution Y of an algebraic differential equation is said to be D plus solvable if Y belongs to a tower of differential fields where Ki is a finite algebraic extension of Ki minus 1, or Ki is a Picard-Hewitt extension of Ki minus 1 for a linear differential equation L of t equal to B over Ki minus 1 of order less than equal to D. And a D plus solvable solution is called D solvable if into B equal to 0. So basically, D plus solvable means you can have inhomogeneous equation of order less than equal to D, but in D solvable, only homogeneous equations are allowed. And we prove this result. So let Y be a solution of an algebraic differential equation over K of order D less than equal to 4. So we restricted to algebraic differential equation of order less than equal to 4. And if Y is also a solution of a linear homogeneous differential equation L of t equal to 0, then Y is D plus solvable for D equal to 1, and it is D solvable for 2 less than equal to D less than equal to 4. And if L is happen to be irreducible, then L of t equal to 0 has a basis of D solvable solution. So this D plus solvable for D equal to 1 and D solvable for 2 less than equal to D less than equal to 4 is basically for D greater than equal to 2, D plus solvable is same as D solvable. But for D equal to 1, it is not. And a nice remark of this result is that if an irreducible linear homogeneous differential equation has a solution y such that its transcendence degree is less than equal to 4, which is I assume D and D less than equal to 4, then the differential Galois group of L of t equal to 0 is a D-solvable linear algebraic group. So what is D-solvable linear algebraic group? A D-solvable linear algebraic group is an algebraic group having a chain of normal subgroups where each of the quotient is a subgroup of GLD. And for D equal to C, we have a counter example comes from accessional group G2. I'll explain briefly the idea of the proof of this theorem. And basically, this theorem uses the full potential of our proof of the main theorem on differential subfield of Picard-Hewitt extension. And we do have a better understanding of the differential subfield of Picard-Hewitt extension whose transcendence degree is less than equal to 4. So let E be the Picard-Hewitt extension of K for this equation of t equal to 0. Since Y satisfies an algebraic differential equation of order less than equal to 4, its transcendence degree will be less than equal to 4. So we have a transcendence, have a differential subfield of Picard-Hewitt extension of transcendence less than equal to 4. Then we saw that this differential field can be embedded in a tower of differential fields where each component is either generated by solution of a linear differential equation of order less than equal to transcendence degree, or it's a irreducible differential subfield of Picard-Hewitt extension of Ki minus 1, whose differential Galois group is one of these following: SL2, SL3, SP4, SL4, or SL2 product SL2. So in the case 2, so case 2 is basically differential subfield of Picard-Hewitt extension whose Galois group is a semi-simple algebraic group. And in case 2, we need classification of affine homogeneous space of dimension less than equal to 4 obtained by Popov and others. And we don't know D equal to 5 because of we don't know this classification of affine homogeneous space of dimension 5. So why this affine homogeneous space comes? Because a semi-simple algebraic group can have a maximum subgroup which is reductive, and if you have a reductive subgroup of a reductive group, then the quotient space is the homogeneous space is affine. Okay. The next result is an extension of the Rosenlitz proposition. So let K be an algebraically closed differential field, and let F and M be a finitely generated differential extension of K, and the constant of F is assumed to be C, the field of constant of K, and F and M are free over K. If Fm contains a constant not in M, then there exists a differential subfield L such that L is either generated by solution of a recurrent differential equation or L is an abelian extension of K. And if K has trivial derivation, that is K equal to C, then L is either Cz or Z prime equal to 1 or Cz with Z prime equal to Cz. So basically you have an abstract generalization of the Rosenlitz proposition, and the Rosenlitz proposition is basically K equal to C, F equal to Cy with Y prime equal to f of Y, or F is a non-rational function. And the proof of this theorem is actually an application of some results proved by Umemura in this article, second proof of the irreducibility of first differential equation of Penn-Levy. So it's an application of Umemura's result together with our structure theorem. Next is the differential algebraic dependency of solution of an algebraic differential equation. And for that, we need this setup. So let f of t prime tn equal to 0 be a differential equation over k, and y be a solution of A, and we consider this set S K F Y. Here U is a universal field extension of K, and we consider all those solutions satisfying the following three conditions. The first condition is that if y1 belongs to S K F Y, then there is a differential isomorphism between ky and ky1 that maps y to y1. And second condition is that for any y1, y2, ym in this set, the field of constant of k differential field generated by y1, y2, yn is C. And the third condition is that the transcendence degree of k, y1, y2, ym over k is the sum of transcendence degree of the individual. So basically, this SKFY, we are looking at solutions whose transcendence degree is same. We are looking at solutions in a no-new constant extension. And the third condition is the solutions are independent. It's not algebraic independent, but some derivatives also independent until some point. And then we prove this result. So let K be an algebraically closed differential field and Y be a non-algebraic solution of this algebraic differential equation. Then this set SKFY is finite if and only if the solution field Ky contains a differential subfield which is either generated by a solution of a recurrent differential equation or it's an abelian extension of K. And if order of the equation is less than equal to 4, then we have a bound of this set which is less than equal to bound of the cardinality of this set which is less than equal to n plus 2. And if K has trivial derivation, that is K equal to C, then this set is singleton if and only there is a differential subfield F of the solution field Cy, where F is either an abelian extension of C or F equal to Cx, or x prime equal to 1 or x prime equal to Cx. So the second condition, the second part of the theorem is basically an autonomous algebraic differential equation or an algebraic differential equation over C has either one or infinitely many algebraically independent solutions. Okay. Next, I will talk about the previous theorem in the case of a first order differential equation. So The first order differential equation are extensively studied in these two articles. The first one is our works, a classification of first order differential equation, and the second one is by Nordben, Vanderpoot, and Tau about, and it is basically they only concern about autonomous first order differential equation, and in both the article, a first order differential equation f of t prime equal to 0 over k is called general type if it has no non-algebraic solution in any iterated strong normalization of k. And then the following statement follows from the previous theorem. A first order differential equation over k is not of general type if and only if it has at most 3 algebraically independent solutions in any given non-new constant action of C. And if k equal to C, then the number is 1. And the second statement is basically a contrapositive statement of the first. General type first order differential equations are precisely those equations f of t prime equal to 0 having a non-algebraic solution y such that set S K F Y is an infinite set. So the first statement is what we asked in our paper, and now we have a proof of this result. And the second statement is what has been expected in the Vanderpoot paper, where they have a nice um, way to see this statement with these abstract solution replaced with power series solutions, and but they can only verify this second statement so for some particular differential equation. And here we show that this is true for all general type equations. And next is about the solvability of algebraic differential equation in a iterative strong normalization. So if we have this rational type equation, Tn equal to f t prime Tn minus 1, this differential equation has a solution y in a iterative strong normalization of k, then ky contains an element z such that Z is a non-algebraic solution of a recurrent differential equation over K. And if K equal to C, then Z can be chosen so that Z prime equal to 1 or Z prime equal to CZ for some C, for some non-zero C in C. And we apply our result to Poisson differential equation and Lotka-Volter system. So for Poisson differential equation, your equation of this form t double prime equal to t prime f of t, or we assume f to be a non-zero rational function. Then this equation has a generic solution. So it has a transcendence degree 2 solution if and only f is not a derivative of some g in Ct. And the equation has and this equation has no generic solution in any iterative strong normalization of C. And for a generic solution Y, the set is infinite. The set is CPY. And for Lotka-Volter systems, which is T1 prime equal to alpha T1 plus beta T1 T2, T2 prime equal to gamma T2, delta T1 T2, we saw that the system has a generic solution in a iterative strong normalization of C if and only if alpha equal to gamma, if and only if the solution belongs to an elementary extension of C. And for alpha not equal to gamma, for any generic solution of Y, the set is of this Lotka-Volter equation is infinite. Yeah. So that's all I have. Thank you for that. See some references.
Thank you very much, Partha, for your very nice talk. Are there questions or comments from the audience? Please just unmute yourself or write in the chat. Okay, any questions or comments for Partha?
Excuse me, maybe I have a question. Yes.
Yeah, please go ahead. Hi, Terry.
So you build this strongly normal extension with this Weierstrass equation. Can you make something similar with abelian varieties and differential connection with several variables? I mean, you define take a genus 2 curve and then so there are two derivations. This defines also some strongly normal extension, but with several derivations.
Are you talking about this result?
Beginning, yes, here, yes. So
Uh,
you have something with genus 1 only. Can you do something more with higher genus?
No, so for transcendence degree one, higher genus can be possible, but but like uh, and Jacobian, so a transcendence degree two differential subfield can be comes from a Jacobian of a genus greater than equal to 2 curve or genus 2 curve transcendence degree two differential subfield comes from hyperelliptic curve of genus 2. That can possible because that is the result of Covices that there are those equations. He has a set of equations where he proves that those equations has differential Galois group, the Jacobian of the hyperelliptic curve. So transcendence degree one is not possible, and one of the reason for that is that if you have an algebraic group and if it has a uh, so and so transcendence degree one differential subfield basically gives you a dimension one homogeneous space, and dimension one homogeneous space of an algebraic group is basically either genus 0 or genus 1.
Okay. Okay, thank you.
Are there further questions or comments?
So I have a question. Uh, okay, it's very naive and easy question. Do you think that you may apply your techniques to study the same kind of question for difference equation?
I I don't know. I thought about it at least for this solvable Picard-Hessier extension, in difference Picard-Hessier extension, but I don't know. But yeah, I'm reading about those. Yeah.
Thank you.
Any further comments or questions? This does not seem to be the case. So we thank Partha again. Thank you very much for your very nice talk. And maybe one short announcement. We think about shifting the time, the starting time for the seminar back one quarter of an hour. So we might in the future start at 10 a.m. New York time. So please watch out for the invitation that you receive from Ronnie. Okay, then thank you again and hope to see everyone back next week. Bye.